All right, everybody. So this is attempt number 2 at doing this discussion recording because the Zoom recording apparently didn't record the screen that was being shared. So we're trying this again, even though the screen was shared. So I don't know what the issue was, but we'll do this again, and it should be a pretty short recording because I only have 2 examples, and I'm going to go over the format of the exam. Okay, so today I'm going to go over gravity, black holes, Kepler's laws, one of Kepler's laws, and adjacent to black holes, tidal forces. Okay, these 3 things, black holes, Kepler's laws, tidal forces, are not on the exam. Okay, so they're just for us to practice. We're not going to be expected to do them on the exam. For gravity, you need to know the forces of gravity in terms of the gravitational constant G, right, big G. And you should also keep in mind the other form of gravitational potential energy, which is negative big G mm over R. Okay, so just keep that in mind. In terms of the exam, though, right, it's going to be 4 questions, right, and they're going to be 2.5 points each. So that's a total of 10 points. It is cumulative. There's going to be 2 bonus questions, and one of them is 1 point, and the other is 2 points. All right, so the max you could get is a 13 out of 10. All right, so you can't get over 100 technically, but the bonus questions are there to help you. Okay, it's going to be 3 hours on Friday over Zoom. Okay, so you have to sign into Zoom. All right, because I'm going to be proctoring the exam on Zoom, and it's from 10 to 1. Okay, if you made prior arrangements with the professor, that's going to be something completely different. But this is for everyone. The exam is on Friday over Zoom from 10 to 1. All right. We have a review tonight, which will probably be right after this gets posted because it's already 4:30, and I didn't realize the other one was broken until now. But it's from tonight from 6 to 7. Okay. That's all the stuff for the exam and stuff. So I'm going to quickly go over these examples. There's only 2. It's the last 2 questions on the homework, so that way you all know how to do them. All right. So the first one is, imagine we have a black hole with a mass that we know. Okay, we don't know the radius of the black hole. And then let's say we know that we have a satellite that's orbiting the black hole center, and it has 2 solar panels with the same mass. The first question of that problem is asking you to find the Schwarzschild radius of the black hole. Okay, the Schwarzschild radius of a black hole is the radius where if we shine a beam of light at our black hole, the light is going to be bended by gravity and fall into the black hole. Okay, if you fall past the event horizon, even light can't get out of that. If you're outside the event horizon, light is going to bend around the black hole, so it won't fall into it. That's what denotes that. And the equation's in your book, but it is 2 times the mass of the black hole times the gravitational constant divided by c squared. And you'd use 3 times 10 to the 8th meters per second, which is the speed of light, so that's c. And the mass of the black hole is given in the problem. So you only need to plug those in, and then you can get the radius of the black hole, right, in meters. And you can convert that to stellar radii or kilometers, whatever you want to do. Right? Part B is a little more complicated. It wants you to find the tension between the solar panels. All right. Okay. So to do that, we need to look more closely at our little satellite here. And we're going to imagine these solar panels are point masses and that they are both a distance d from the center of the satellite. Okay, I think in the problem it's 1 meter. But there's two ways of doing this. There is a fast and easy way that is less accurate and more prone to error, but there is a more complicated way that is more accurate. So you can do it either way. The easier way is going to be doing it delta Fg, finding the change in gravitational force between the top solar panel and the bottom solar panel. So you can do Fg bottom minus Fg top. That's going to give you a positive number because the gravitational force up here is going to be less than the gravitational force down here. The reason is because the bottom solar panel is closer to the black hole, so it has more gravity acting on it. Okay? So to do that, you just do Gm times the mass of the solar panel, where big M is the mass of the black hole, divided by the bottom is going to be R minus D squared, where this is the source, the radius of the orbit, and then the top would be R plus D squared. Okay? And you could simplify this if you wanted to be this. Minus 1 over R plus D squared. And this could be your answer. You could plug in all the values. All of these values are known. Okay? All right, the other way is going to be to actually use conservation, force conservation, okay? So the satellite is orbiting a black hole, and the reason this method is going to be better is because it's going to account for your centripetal force. Since it's in an orbit, you have a centripetal force here. So that means you have a net force towards the black hole. Okay? Down here, your centripetal force is going to be the same as up here because they're connected to each other. So the net force has to be the same along the entire body of the satellite. Meaning, for the bottom, you're going to have Fg of the bottom minus tension is equal to the centripetal force, mv squared over r. And for the top, you're going to have Fg top minus tension is equal to mv squared over r. Right? And so what we can do is we have two equations. We have two unknowns, right? We don't know what V is. We don't know what tension is. We want to solve for tension. So you can solve one equation for V squared. And if you do that, you could get something like Gm black hole over R plus D minus Tr plus D over Ms is equal to V squared. And then you could plug that in to the other equation. So I solved for the top satellite here, or solar panel. Sorry. Solar panel. And I'm plugging in to the equation for the bottom. And if you do that, you should end up with something that looks like this. All right. You don't have to simplify it because all of these numbers, all of these quantities would be known. So you could just plug them in. All right. So this is as simple as we would need to be. Okay. So something like that. And you can see this will give you a slightly different answer most of the time. All right. But this is showing, right, we have a tension force between the two satellite solar panels. The reason behind that is because gravity is acting at a different magnitude to the top solar panel because it's further away than to the bottom one. It's closer. So when you're orbiting the Earth, there is still a change in gravity for those two positions, but it's so small because the Earth's mass is so small. But a black hole has a really tiny radius, so you can get very, very close to it. And it has a very, very big mass. So the force due to gravity can change very wildly, right? Because it depends on the mass of the black hole, the mass of U, and then over r squared. So if r is already small, and we get a little bit closer, the force due to gravity is going to go up a lot because it's r squared in the denominator. So if you lower that, you're dividing by less. So your force due to gravity is going to be higher. Okay, so this still applies like even if you were on Earth, like I said. So like when you're on Earth, your head experiences less gravity than your feet by a difference of h. But the difference is going to be much, much smaller than if you had a black hole, for example. All right. The other example I wanted to do was from problem 13.67 in your book, which is what the one orbiting satellite problem around the Earth is from. I basically took the question from the book and changed a few things. But we can do this one, okay, because it'll be basically the same as your homework problem. So we have the perigee and the apogee. One of them is 400, one of them is 4,000 in the book. All right. And part A of the question in the book asks you to find the orbital period. Period, not going to be on the test, but its variable is T. Okay, so this T is different from tension T. This is a different variable. And the equation for that is Kepler's third law, which says that the period squared is equal to 4 pi squared over the gravitational constant times the mass of the thing you're orbiting times a cubed, where a is your semi-major axis. Okay? So, a semi-major axis, what that is if all orbits are ellipses, so let's imagine this is the Earth, okay? The radius to the perigee is here. The radius to the apogee is here. You have two axes on an ellipse. You have a minor axis, which is the minimum distance, the minimum diameter, and you have a major axis, which is the longest diameter. So the major axis is the radius to the perigee plus the radius to the apogee. The semi-major axis is just it's the radius. So it's half of the major axis. It would be this blue line here. Okay. So the major axis would be 2a, which means 2a is equal to rp plus ra, meaning the semi-major axis is rp plus ra divided by 2. All right. You can notice this RP and RA are different from the variables I put up here for the heights of the orbit. If you're given an orbit, usually it's with respect to the surface, okay? But the semi-major axis is with respect to an arbitrary point at the center of an ellipse. So you need to account for the radius of the Earth too, all right? So RP is going to be HP plus the radius of the Earth. And then RA would be HA plus the radius of the Earth. Because you have to account for that. All right? So, now that we have that, we can find T, period. The period T. So we have T is equal to the square root of 4 pi squared over GM, A cubed. And we know A would be equal to radius of the Earth plus height of perigee plus height of apogee over 2. All right, so you can plug that in. And you would have this, right, like this, divided by 2. This would be cubed, and this is over gm. This is all square rooted here. And that would be your answer. Okay? So, just keep that in mind, that when you're finding your semi-major axis, if you ever do this in the future, that you're accounting for the actual radius of the body you're orbiting. All right? And if you plug in the numbers given here, so HP is 4,000 or 400 and HA is 4,000, you would get a period of about 7.91 times 10 to the third seconds, which is about 2.2 hours. Okay? All right. Part B says, using conservation of angular momentum, find the ratio of the spacecraft's speed at perigee to its speed at apogee. So we need to find the ratio of speed at perigee to apogee. Okay, so momentum is going to be conserved in this instance because there is no outside work being done on the spacecraft. It is bouncing between kinetic and potential gravitational energy. When it's at perigee, it has maximum kinetic energy. When it's at apogee, which means furthest away from the planet, that's the maximum gravitational potential energy, or technically the minimum because it's negative. So it's converting that kinetic energy into gravitational potential as it moves away in the orbit, and as it gets closer to the planet Earth, it gains speed, gains kinetic energy. All right, so Li is equal to Lf, angular momentum is conserved, and for that we can basically just convert, and I will say Li is the perigee and Lf is the apogee, okay? So we can convert from I and omega into M, V, and R using the relationships in the table I gave you all. We're just going to approximate the spacecraft as a point mass, so I can just be MR, all right? But this would be MVP RP is equal to MVA RA. So perigee to apogee means top over bottom. So velocity of perigee over velocity of apogee is equal to the radius at apogee over the radius at perigee. Which makes sense, because the velocity at perigee is higher than the velocity at apogee, right? And the radius at apogee is higher than the radius at perigee. So both of these fractions would be greater than 1. Right? And they're about 1.531. Okay? Okay, so we're going to keep this in mind for part C, right? We're going to need this relationship. You can find it another way if you want, but it's just easier if we just keep this in mind for part C. So for part C, it says, using conservation of energy, find the speed at perigee and the speed at apogee. So now, instead of using conservation of angular momentum, we're going to use conservation of energy to find the actual values of VP and VA. All right. So you can do this without even doing this part B. And I'll show you how to do that. But we basically have an equation of conservation of energy. So the kinetic energy at perigee plus the gravitational potential energy at perigee is equal to the kinetic energy at apogee plus the gravitational potential energy at apogee. So 1/2 mvp squared plus minus g, mass of the Earth, mass of your satellite, divided by radius perigee is equal to all of this. Same thing for apogee over here. Okay. I'll move all the kinetic energy stuff to one side. So we would have Vp squared minus Va squared is equal to 2g mass of the Earth 1 over Rp minus 1 over Ra. All right. This is all known. And if you plug in everything here, okay, this would be equal to 1.531 squared. Okay, so that's the other way of finding this. And so now what you can do is you can say, okay, Vp squared is equal to 1.531 squared Va squared. Okay, we know we can now plug this in as Vp up here and solve. So if you do that, you would get Va is approximately equal to 5.51 times 10 to the third meters per second. And then you just plug this back into this equation here. I'll call this star. And if you plug into that into equation star, you would get velocity at perigee is approximately 8.43 times 10 to the third meters per second. Okay? Those are your two velocities. So the velocity at perigee is higher. It's closer to the Earth. So you have a greater velocity. Okay? The last part, part D, says it's necessary to have the spacecraft escape from Earth. If the spacecraft's rockets fire at perigee, how much would the speed have to be increased by to achieve this? What if the rockets were fired at apogee? Which one in the orbit would be more efficient? Okay, so to escape the Earth, right, if we're going to fire at perigee, that means that we're at the closest value, closest radius that we could be to the Earth. So if we want to fire our rockets, let's say our rocket is here, okay, and we're moving counterclockwise, right? We're going to try and fire our rockets opposite to the direction of movement because that's going to speed us up. So we're going to increase our orbit until we reach a point, or increase the apogee distance until we reach a point where the total energy is zero at that point. And that's because, okay, we're going to expect it to be zero. Why are we expecting it to be zero? Well, we're going to expect the potential energy due to gravity to go to zero at that point because the radius at apogee is going to be going to infinity. Right? We're escaping the Earth. So that means we're not going to be orbiting it anymore. We're going to be at an escape trajectory. Okay? So how do we know that? Well, remember, the gravitational potential energy equation is negative Gm little m over r. So if r goes to infinity, this is like Gm m over infinity. This is limits, which we're not expected to necessarily know, but if you've done them before, you can see this equation would go to zero if you take the limit of that as it goes to infinity. You're dividing a number by basically a ginormous number, which is going to make it very, very small, very, very close to zero. And as r approaches infinity, it does reach zero. For kinetic energy, we're also going to expect that to go to zero because 1/2 mv squared is the equation for kinetic energy. Well, at apogee, we want the velocity to be zero when we're escaping because at our maximum distance from the Earth, the velocity should be zero because all of the energy should be converted into, it should have been used to get us out of the gravitational well, okay, to escape. So V is going to go to zero. We're going to take the limit as V goes to zero, and you can see this also equals zero. So that means our conservation of energy equation would be Ke perigee plus U perigee is equal to zero. Or 1/2 mvp squared and Vp escape. So we're going to take the escape velocity squared minus Gm little m over r perigee is equal to zero. And we can solve for this. Okay, so Vp escape would be equal to Gm Earth times the mass of the rocket over RP times 2 divided by m, because the mass is on both sides, the mass of the rocket is on both sides, so it gets canceled. And this is squared, so we take the square root of both sides, and we would have the escape velocity at perigee would be the square root of 2g mass of the Earth divided by the radius at perigee. If you plug in all those values, it should give you about 1.084 times 10 to the 4th meters per second. So the change in velocity needed would be the velocity that we need to escape minus the velocity that we already had at perigee. And if you plug those in, that gives you about 2.41 times 10 to the 3rd meters per second. All right, so we need to increase our velocity by 2.41 times 10 to the 3rd meters per second using rockets to do that. Delta V is what that's called, or delta V. For perigee, it would be this, okay? These two numbers. The escape velocity would be this one, and then our delta V at perigee would be this. For apogee, it's going to be a little different. It would be the same exact, you would do the same exact equation, you would just plug in RA here instead of RP. And if you do that, the escape velocity at apogee would be about 8.761 times 10 to the 3rd meters per second. Okay, so a higher escape velocity is needed. And the delta V would be even greater still. So it would be 3.25 times 10 to the 3rd meters per second. All right, so we need a higher escape velocity, and we need more delta V. So that means that it's better to fire your rockets at perigee because we need less delta V. So we have to impart less impulse, because remember, your impulse J was delta it's your delta P, your change of momentum, which is m delta V. So we are doing less, we have to put less force over time to do that. So we're doing less work if we do it at perigee. And perigee is actually the most efficient place to fire your rocket if you want to escape the system. Okay? Because you're already, the opposite direction to that would be the apogee, which is your highest distance from the Earth already. So you're just going to increase that. You only have to increase that a little amount. Less amount to get to the escape trajectory. But if we're on the apogee side, the opposite opposing side of that would be perigee. It's closer to the Earth than you already are. So you have to get it up to where you are first, and then you have to move past where you are to increase the velocity. Okay? All right. So, with this stuff, right? Part A, not going to be on the exam for this question, okay? Part A of this question. However, part B, C, and D, those are, like, important for the exam, because you're going to have to know, like, conservation of momentum, conservation of angular momentum, conservation of energy. Those could be on the exam, right? It's just this Kepler's law won't be on the exam, okay? And as for this other problem, same sort of thing. The Schwarzschild radius, not going to be on there. But a problem where you have to find forces, we've done that before. We did that towards the beginning of the quarter. So that could be, a question like that could be on the exam, but not finding the Schwarzschild radius or anything. Okay? All right. So that is the recording. Hopefully a little shorter because I've had time to kind of condense a lot of things. But like I said, the exam is on Friday at 10 o'clock. You have to be there, okay? You have to join the Zoom meeting. If you're not in the Zoom meeting, you're not going to be able to have the exam graded. Okay? So you need to make sure you're in the meeting because I'm proctoring the test. Now, I'll be able to answer any questions you have about the test that are related to like clarification. So if you're unsure about a diagram or how something is written, or if you see an error somewhere, let me know and I can answer a question about that. Hopefully there are no errors about this test. Okay. There shouldn't be, but it should be relatively smooth. So you only have 4 questions, but you have 3 hours. Right? And I did 2 of the questions. The professor did 2 of the questions. All right. And the professor did the bonus questions. Okay. So we're going to have a review in an hour from now, almost. So I will see you then. But thank you. And if you have any questions before the exam, send me an email.